tap is probably one of the simplest actions that we perform every day. But have you ever asked yourself what happens to water before reaching our tap? The management of drinking water supply systems from the freshwater source to the treatment plant and the distribution network before reaching our tap is very complex. However, this is essential to achieve sustainable drinking water supply and increasing citizen safety more and more. These objectives are included in many of the United Nations Sustainable Development Goals, such as the provision of safe water, good health, the development of sustainable smart cities, and the improvement of consumption patterns. If you are thinking that sustainable and safe drinking water supply is an issue only in developing countries, this is not true. In fact, this is a problem even in developed societies due to a heavy anthropic pressure that impairs the safe use of water. In industrialized areas as well as in highly urbanized areas, water sources are often contaminated by a wide variety of conventional and emerging contaminants, such as perfluorinated compounds and pharmaceuticals. Among emerging contaminants, only few of them have been considered in the recent revision of the European Directive on Drinking Water, while a relevant number of compounds is still unregulated. This is due to the still existing high uncertainties on exposure levels and actual health effects, which make it difficult to evaluate their potential health risk for consumers. Now, let's have an insight about how drinking water supply systems are organized, having in mind that the quality of drinking water is regulated by European national regulations. The water resources we can use for drinking water supply are rainwater, fresh inland surface water and groundwater, saline and brackish water. Rainwater has historically been an important source, also influencing the architecture of houses, especially in arid and semi-arid regions, including roofs for water harvesting. Saline water is the most difficult source to exploit for human consumption, as it requires the reduction of salt content. Only in the recent decades, saline water has increasingly been used thanks to the development of a specific treatment process, namely reverse osmosis, which allows the removal of salts without going through evaporation condensation as done in the past. Therefore, the most widely used sources for drinking water are spring water, groundwater, and surface water, namely river and lake water. The chemical and microbiological characteristics of these water sources are considerably different, leading to different water supply systems. Let's talk about groundwater, specifically about characteristics and contaminants which affect human consumption. The chemical characteristics of groundwater depend mainly on the depth of groundwater level and the composition of the soils they flow through. In general, mainly shallow aquifers are subjected to organic and inorganic pollution due to anthropic activities. Typical organic contaminants of anthropic origin are related to industrial and agricultural activities, such as chlorinated solvents, polycyclic aromatic hydrocarbons, pesticides, flame retardants, and their transformation products. As for inorganic contaminants, they have both natural and anthropic origin. For instance, heavy metals such as chromium, iron, manganese, and nitrate, ammonia, and arsenic from fertilizers. It is important to stress that, contrary to organic contaminants, some inorganic contaminants are considered as such only for their impact on organoleptic properties of water, that is, color, taste, and smell, having no significant impact on human health, as in the case of iron and manganese. Regarding microbiological characteristics, with the exception of shallow aquifers, groundwater is usually protected from microbial contamination, such as microorganisms of fecal origin as E. coli and fecal coliforms. Moving on to surface water, let's have an insight about which characteristics and contaminants affect human consumption. Surface waters have more common characteristics than groundwater. We can group these characteristics in three main classes: natural organic matter, suspended solids, microorganisms. The first two are mostly related to organoleptic properties and the management of treatment processes rather than to human health. Regarding microbial contamination, surface water is highly vulnerable to fecal contamination related to both animals and humans. We also have anthropic contaminants, which are essentially organic compounds, such as pesticides, which derive from agricultural fields runoff, and emerging contaminants, such as pharmaceutical and personal care products, endocrine-disrupting chemicals, which are not well removed in wastewater treatment plants and therefore enter the aquatic environment, potentially impairing freshwater sources. It is important to stress that organic compounds of natural origin are present in water at concentrations of several milligrams per liter, while organic compounds of anthropic origin are present at concentrations of 1 or 2 orders of magnitude lower, that is micrograms or nanograms per liter. Despite their low concentrations, they might pose a danger for human health. Now let's turn to how we can remove contaminants from supplied water, understanding the structure of drinking water treatment plants. Drinking water treatment plants are composed of a sequence of operation units, each one specifically devoted to the removal of selected contaminants. Therefore, based on the type of water supplied, the contaminants present, and their concentration compared to the list of legacy parameters, it is possible to select the most suitable operation units to form the treatment train according to predefined rules. To simplify, it is like a construction game composed of different pieces having specific shapes that cannot be randomly combined together, requiring a perfect match to obtain the final construction. Summarizing, multiple contaminants are usually present at even very different concentrations and having different chemical properties and physical forms. Hence, the definition of a treatment train is challenging, since each group of contaminants requires different removal extents and different removal processes to assure safe drinking water. Let's focus on drinking water treatment plants fed by groundwater. Since one or few contaminants are present at the same time and given the wide range of potential compounds, treatment plants are highly diversified, but usually very simple, being composed of only 1 or 2 operation units. The most common operating unit is devoted to adsorption of activated carbon, which allows to transfer organic contaminants from water to the surface of the porous particles of granular activated carbon used in fixed bed filters. Frequently, after the operating units devoted to the removal of organics and inorganics, disinfection is applied to ensure microbiological safety of water prior entering the distribution network. Talking about drinking water treatment plants fed by surface water, treatment plants have a fairly widespread conventional scheme aimed at removing the typical contaminants present in surface waters. After a preliminary settling to aid the removal of suspended solids during flood periods, the treatment train includes a clarifloculation unit to remove colloidal solids and organic matter, a filtration unit to remove residual turbidity, an ozonation unit to reduce both disinfection byproduct precursors and microbial contamination, an adsorption unit on granular activated carbon to remove anthropic contaminants and residual disinfection byproduct precursors, a disinfection unit to inactivate pathogens. Once drinking water has been produced, it enters the distribution network up to our taps. We can drink, cook, wash, being aware that tap water is safe and sustainable.